So far in this course, mainly we dealt with Lebesgue measure on R and Lebesgue integration theory again on R. Now what I want to briefly explain is that the theory that you developed in Lebesgue measure and Lebesgue integration can be carried over to a general setting in a general measure space, and you can talk about integration over a general set, need not be R, provided in that set you have something similar to Lebesgue measure. If you recall, this is what you called as abstract measure and abstract integration. If you recall, in the first few lectures, in fact, we dealt with this, not with Lebesgue measure on R and Lebesgue integration. What we dealt with was abstract measure space. We started by explaining an intuitive approach to measure. We started by asking what is measure theory, what is our experience so far in measuring length, area, volume, etc. Then looked at the properties of length, area, etc. And then we made some axioms and so on. And finally, we end up with sigma algebra and measure. Okay. And we have seen that the requirements in sigma algebra and requirements in measure go hand in hand. Okay. As I told you, I just wanted to put those things at one place. So I have collected those things as a note and I have not uploaded it yet. I thought of sharing with you in this lecture before uploading. Okay. So the first part of this lecture is just to show you that notes which I have written from our experience in Lebesgue measure and Lebesgue integration theory, and also some definitions we made in the first few classes like sigma algebra, measure, etc. Okay. Are you with me?
Yes, sir.
So now we are in abstract measure space and we want to define abstract integration, not just integration on subsets of R. Okay. So these are certain things we did in the initial classes, that we looked into what are the requirements of measure and so on. And finally, we were led to the definition of sigma algebra. So I have once again reproduced it here for you. Given an arbitrary set, need not be R, you can consider a family of subsets of X, possibly the power set of X or a subset of power set of X. If you want to declare that family as a sigma algebra, we need certain requirements. That family of subsets of X should be rich enough. Rich enough in the sense it should be closed under complementation. Whenever a set is there in that collection, the complement should also be there in that collection. That collection should be closed under countable union, and so on. Okay. Such a collection is called sigma algebra, and a set along with a sigma algebra is called measurable space. All this definition we made in the first few classes. So something like a topological space, which is subject of study in topology, a pair x comma tau, where tau is collection of subsets of x and tau satisfy certain requirements. In a similar manner, in the measure theory, the subject of study is a pair x comma script A, where script A is a suitable collection of subsets of x. And that pair is what is called as measurable space, and elements of A is called measurable sets. They are called measurable sets. Something like elements in a topology are called open sets. So the first ingredient of measure theory is a measurable space. What is measurable space? It is a pair, a set X and a collection of subsets of X. Okay. Is that okay?
Yes.
Do you have one example? Of course, you can give variety of examples, but one standard example is take X to be R and consider the collection of all Lebesgue measurable subsets of R. I repeat, take X to be R and script A to be collection of all Lebesgue measurable subsets of R. And remember, Lebesgue measurability comes via outer measure and so on. First, we have Lebesgue outer measure. Then we define a splitting condition or Carat-Theodore splitting condition. And we collect those sets which satisfies the splitting condition and call them measurable sets. And collection of all Lebesgue measurable set is a sigma algebra. Okay, so instead of R comma set of all Lebesgue measurable sets, now we have X comma script A, where script A satisfy the requirements closed under complementation mainly and closed under countable union. Okay. Now, given a measurable space, what is a measure? A measure is a way to assign a number with each elements in this sigma algebra. That means each sets. For each set, I want to have a number and I want to quantify that set. Something like length and open intervals. For each open interval, you can talk about length. Okay. In a similar manner, for each element in a sigma algebra, the collection of that subsets, we can talk about a number. And to assign a number, we seek help of a function. And that function is called measure. Okay. So measure is basically a function from sigma algebra A to 0 infinity. Okay. And to call it as a measure, it should satisfy certain requirements. And that requirements are governed by our own experience with measuring area, volume, length, etc. Okay. So there are basically two requirements. Measure of null set is 0 and measure of union AN is equal to sum of the measure. Okay. Measure of the whole is equal to sum of the measure of the parts. Okay. Provided these parts are disjoint. And once you have a measure, the triplet is called a measure space. X, sigma algebra, and a function mu satisfying this condition is called a measure space. And that mu, the function, is called measure. Is that okay?
Yes, sir.
We have defined all these things in the first few lectures. Now, do you have a good example for a measure space? Can somebody tell me one example for a measure space? No, I have written over there. It's very disappointing to see that you don't respond to the questions, that too a trivial basic questions. Okay. Do you have an example for a measure space?
Yes, sir.
What is that?
Set of real numbers and
Yes.
set all Lebesgue measurable sets and measure Lebesgue measure.
Lebesgue measure. So this is our prototype example, or scriptium M. Scriptium is collection of all Lebesgue measurable sets, which comes via outer measure, Carathéodory splitting condition, and so on. And you restrict the outer measure to collection of all measurable sets, then you get what is called as Lebesgue measure. Okay. So that now turns out to be just one example. But now I have noted there a few examples, and most of these examples were either introduced in the beginning of this course or I have introduced via tutorial 1 or 2. Okay. For instance, take any non-empty set, a trivial example, and take script A to be null set and this non-empty set, null set comma X, and define mu as follows. Mu of null set equal to 0. We don't have choice. That is one requirement. And mu of X I defined as 1. Okay. Then you can see that this triplet X comma A comma mu satisfies all requirements for a measure space. Okay. Please try to distinguish between measurable space and measure space. Measurable space is a pair, a set comma sigma algebra, and measure space is a triplet, a set comma sigma algebra comma function or measure. That is called a measure space. Okay. Another example is here, that is usually called counting measure. From the name, it should be clear. What we do is we count the number of elements. We count the number of elements. Okay. Take a non-empty set X. Define script A as power set itself. In the most ambitious case, script A would be the whole power set. Okay. In the Lebesgue measure, we have seen that not every subset of R you can measure. That's why we did not take 2 power x. We went for a subset of 2 power x in the case of Lebesgue measure on R. Okay. But in the most ambitious case, we can take A to be the whole power set of x. And what is the measure? Measure of a set E is number of elements if E is finite set. Otherwise, you define it as infinity. And remember, by definition, measure can be infinity. Mu is a function from sigma algebra to collection of all real number along with the symbol infinity. Okay. So this is again an example of a measure space, and mu is called counting measure for obvious reason. Is that okay?
Yes, sir.
I have given another example here. Again, it is in a general setting. You start with any arbitrary set, maybe non-trivial set, non-empty set to start with, so that everything will become non-trivial. Otherwise, things will be trivial. So you can start with a non-empty set. Take script A to be power set of X, collection of all subsets of X. Now I am going to define measure in a particular way. Fix an element in X naught. Fix an element X naught in X. Okay. And how do I define measure of a set? Let E be the set you want to measure. And I want to define mu of E. I will define mu of E as 1 if this fixed element X naught is in E. If X naught is a part of E, I will define mu of E as 1. If X naught is not in E, I will define mu of E as 0. So this is the way in which I define my measure. And now you can see that the triplet X, A, mu satisfies all requirements of a measure space. This measure has a special name. It is called Dirac measure on the set X centered at X naught. There is an intuitive way to understand this Dirac measure. Okay. So how do you understand this? You think of a wire of negligible weight, something like a thread, which you assume that there is no weight. Okay. And on this, or maybe you can think of it as a necklace without any, it is a cheap necklace made of a cheap thread. Okay. In that necklace, you have a pendant, you have a bead, which is very costly. Let us say a diamond pendant. Okay. Now, you want to measure a part of this necklace. If that part contains no diamond, the diamond is not a part of this, the shopkeeper is ready to give you that necklace free of cost. So the measure is 0. But if the part of the necklace contains this precious pendant, then the shopkeeper will charge you. Okay. And the charge is 1. It may be 1 lakh or 1 crore or some 1 unit. Okay. So this is how you can interpret the Dirac measure. So it's a thread. If you select that part of thread which doesn't contain the precious bead, you can get it free of cost. The measure is 0. But if you are selecting that part of the thread which contains the precious bead, then you will be charged, and the charge is 1 unit. Okay. Is that okay?
Yes, sir.
And this is called a Dirac measure. It's called a Dirac measure. Okay. Now, next semester, you have a course called probability, I suppose. Again, the basic setting comes from measure theory. So a basic setting in probability is a measure space X, A, mu. But one more requirement we put there, mu of the parent set X should be equal to 1. Okay. In general, mu of X need not be 1. Can you talk about mu of X? Yes, because X is an element in script A. Are you with me? By the very definition of sigma algebra, X is an element in script A. Do you agree?
Yes, sir.
Therefore, you can talk about mu of X. But in general, mu of X can be any real number greater than or equal to 0, and it can be even infinity. Okay, but in case mu of x is 1, then mu is called a probability measure. Okay, and this is the setting in probability theory. And keep in mind that Lebesgue measure on R is not a probability measure, because the Lebesgue measure of R is not 1. It is in fact infinity. Okay, but you restrict. For example, instead of R, you take closed interval 0, 1. And you consider the Lebesgue measurable subsets of 0, 1. And you consider Lebesgue measure on that restricted collection. Okay, then what is mu of 0, 1? Mu of closed interval 0, 1? 1. So you will get a probability measure. So Lebesgue measure on R is not a probability measure, but Lebesgue measure restricted to suitable measurable set. For instance, closed interval 0, 1 is an example of probability measure. Okay. Now, instead of mu of x is equal to 1, you just assume that mu of x is a finite number. Then you call the measure as a finite measure. Mu of the total set x is finite. Then you call it as finite measure. Keep again in mind that Lebesgue measure is not a finite measure on R, because measure of R is not finite. So R comma m comma small m is not a finite measure. Okay. Now we have another concept. Instead of finite measure, sometimes we are okay with what is so called sigma finite measure. Now what is sigma finite measure? The parent set X you can write as countable union of subsets, and each of these subset is of finite measure. I repeat, you have a measure space. That means you have a set X, you have a sigma algebra, you have a measure. And the set X you can express as countable union of subsets, measurable subsets, and each of this has finite measure. Then you call such a measure as sigma finite measure on set X. Okay, you have seen that R cryptium small m is not a finite measure. Yes or no? Real
Yes,
number with Lebesgue measure is not a finite measure. The question is it sigma finite? Is it
yes,
sigma
sir.
finite? Yes, because R you can write, for instance, as union of minus n n. So R can be expressed as countable union of measurable sets. Need not be disjoint. Okay. We don't have requirement of disjoint. You can write X as union of Xn. And each of these sets in the union has finite measure. Measure of minus n is 2n, which is finite for each n. Okay. Therefore, the Lebesgue measure is a sigma finite measure on R. Okay. So if you have a measure, say mu, you can multiply that measure with a non-zero real number. Again, you will get a measure. It's something like a scaling. Okay, that's the second thing I have written. I don't have to go through it. That's easy. Now, I have an important example here. So one important example that you have seen for measure is Lebesgue measure on R. Okay. Why only R? You can in fact define Lebesgue measure on R2, R3, R4 and so on. So that is what I have written here. I am defining Lebesgue measure on Rk, where k is greater than or equal to 2. Please recall how we define Lebesgue measure on R. Okay. Starting point were intervals. Do you agree?
Yes, sir.
And we know measure of interval. Namely, you can define length for each interval, and using intervals as fundamental building block, we have defined outer measure for a subset of R. And via outer measure, we went for measure. Okay. So a similar approach you can do not only in R, but for R2, R3, etc. Okay. And that is called Lebesgue outer measure on RK. How do you do? So, for instance, you take R2. So, instead of interval, you take Cartesian product of two intervals. Let us say A1, B1, comma A2, B2. A1, B1 along x-axis and A2, B2 along y-axis. What this Cartesian product will give you?
Rectangle.
An open rectangle, right? So similarly, you do for R3, R4, and so on. You define what is called as hyperrectangle. Okay. So what is hyperrectangle? It is Cartesian product of open intervals A1, B1, comma A2, B2, etc., comma AK, BK. Okay. So instead of open intervals in R, now you have open hyperrectangles in RK. Okay. Now, for intervals, you had a length. Now I am going to define volume for a hyperrectangle. I define volume for a hyperrectangle. For instance, for rectangle, instead of calling volume, I will call area. But in general, I will call it as volume. And how do I define? I define it as product of length of this interval. That is B1 minus A1 times B2 minus A2 times etc. BK minus AK. Think of length of, area of a rectangle, length into breadth in a similar manner. Okay. So you have hyperrectangle and you have volume for hyperrectangle. Okay. Now, with this as basic concept, I am going to define outer measure. For what? Outer measure for subsets of RK. Okay. So let us take E to be a subset of RK. I define M star of E as follows. Remember how we define outer measure for subset of R. Can you recall? How did you define outer measure for a subset of R? Yes. Can somebody recall, remind me how we define outer measure for a subset of R? What was the definition? No, after the entire course is over, you are not able to recall outer measure. We cover this set with open intervals, countable number of open intervals, right? And you take length of this open interval and sum it. And then you take infimum over all such covers. Yes or no?
Yes, sir.
Do the same thing. Instead of length and intervals, now you have hyperrectangles and volumes. Okay. So given a set E, you cover that E with hyperrectangles. That is Rn. Rn's are hyperrectangles. So that unions of Rn cover E. E is contained in union in Rn. Okay. Now you consider the volume of each of these Rn and sum it. Instead of summation of length of In, you have summation of volume of Rn. Now you make this cover better and better. Okay, that by taking infimum. This quantity is called outer measure. This quantity is called outer measure. Okay, so now you have outer measure for a subset of Rk. And there, after defining outer measure of a subset of R, you have seen that outer measures satisfy certain properties. Same thing you can do here. Outer measure of a null set is 0. If A is contained in B, outer measure of A is less than or equal to outer measure of B. Outer measure is monotonic. But unfortunately, even for a disjoint collection, outer measure of the union will not be exactly equal to outer measure of the individuals. You will get only less than or equal to. Whether it is disjoint or not disjoint collection, you will not get outer measure of the whole is equal to sum of the outer measure of the parts. You will not get. Same deficiency we had in the outer measure of subset of R. Yes or no?
Yes, sir.
In other words,
Yes, sir.
outer measure is not a measure. Outer measure is not a measure. Okay. So what did we do then? We consider only those sets which are measurable. Now, how do you define measurable sets? Same way, you call a subset of E as measurable. Sorry, subset E as measurable if for every set A, outer measure of A you can write as split. You can split A into two sets. Any set A, you can slice with this slicer or cutter. The cutter is E. Okay. With the help of E, you can cut A into two pieces, and measure of A you can define as measure of part of A in E and part of A in E complement. If that you can do for every test set A, we call such as cutter E as a perfect cutter or a perfect slicer, or we call it in the language of measure theory, measurable. Do you remember all these things?
Yes.
Yes,
So instead
sir.
of now subsets of R, you have subsets of Rk. Do that and collect those subsets which are perfect slicer, and that I have collected as M. And you can prove that M is a sigma algebra. The collection of Lebesgue measurable subsets of Rk is a sigma algebra. Okay. Now, once you have sigma algebra, now you can talk about a measure. And what I do, just take same as outer measure. Measure is same as outer measure. Only difference is that now I define outer measure not for every subset of R or Rk. I will define only for measurable subsets. Okay. Same thing what you did in R. Okay. Now you will get what is called Lebesgue measure, not on R, but in general for Rk. Are you good with it? Is it okay?
Yes.
Yeah. So this is Lebesgue measure on Rk. Okay. But remember, the Lebesgue measure on R and Lebesgue measure on Rk both come via outer measure. First, we defined outer measure, and then we defined collection of all measurable sets by putting Carat-Theodore splitting condition. You collected all those sets which are measurable. That formed a sigma algebra, and on that sigma algebra, we restricted our outer measure to get a measure. Is it okay?
Yes,
Yes.
sir.
This also you can do in general, not on R and Rk. Okay. From outer measure, you can construct a measure. Okay. This also we have explained in first or second tutorial. Okay. So you have an outer measure. Now what is an outer measure? You have a set X. Outer measure is a function from power set of X to 0 infinity, satisfying certain requirements. Mu star of null set is 0. Mu star is monotonically increasing and mu star is countably subadditive. Countably subadditive. Okay. Subadditivity. So once you have an outer measure, you can define or you can collect those sets which are measurable. Here, which are not Lebesgue measurable, I will call mu star measurable. Okay, how do I define? Put Cartesian condition. Collect all those good slicers, perfect slicers. Collect all those set E which can cut any set into two pieces. Any set A into two pieces. One inside E and one outside E, so that the outer measure of A is exactly coincide with outer measure of that part of A in E plus outer measure of that part of A in E complement. Collect such E's. A is a test set. Collect such E, which I marked as rectangle. Those are like cutter or slicer. Okay. And that family of all measurable set is going to be a sigma algebra. And once you have a sigma algebra, restrict mu star into that sigma algebra. You will get measure. So like Lebesgue measure is constructed from Lebesgue outer measure, in general, if you have an outer measure on a set X, you can define a measure out of it. We can define a measure out of outer measure. Is that okay?
Yes, sir.
Now, if you remember, if you recall R is a topological space. You have a topology on R. Okay. And given any collection of sets, you can define a smallest sigma algebra containing that collection. And that is called sigma algebra generated by that collection. I repeat, given a set and collection of subsets, you can define a smallest sigma algebra containing that collection by taking intersection of all sigma algebra containing that collection. Okay. Given collection may not be a sigma algebra, but you can consider all sigma algebra containing the given collection and then intersect it. Find the intersection. That is called sigma algebra generated by the given collection of subsets. Okay. Now, instead of starting with any arbitrary given collection, you start with the topology. Suppose you are given with a topological space y comma tau. What is tau basically? You are given with a topological space. What is tau basically? What is a topology? What is a topology? Is it a collection of subsets of Y?
Yes, sir.
Satisfying certain condition. Leave about the condition. Anyway, it is collection of subsets of Y. So tau is a collection of subsets of Y. Tau may not be a sigma algebra. Tau is a topology. It will not be a sigma algebra. But you can define a smallest sigma algebra containing tau. And that is what is called as Borel sigma algebra. So if you start with a topology and consider a sigma algebra containing that topology, smallest one, that sigma algebra is called Borel sigma algebra and the elements are called Borel sets. This also we have done in the initial few classes, and thereafter while defining Lebesgue measure, I have defined what is Borel measure, Borel sets, and we have seen that collection of Borel sets is only a sub collection of collection of all Lebesgue measurable sets. Do you agree?
Yes. Yes.
Script B and script M, same thing I am talking about. Instead of starting with an arbitrary set, if you start with a topological space, then you can think of a smallest sigma algebra containing the topology, and that is called Borel sigma algebra, and elements are called Borel sets. So in that sense, every open set will now turn out to be measurable. Okay, because open sets are elements in tau, and every element in tau will be an element in sigma algebra as well, because you are considering sigma algebra containing tau. Therefore, elements in the topology will become elements in the sigma algebra. So every open sets will be measurable. Okay, but not every measurable set is open. So there are two sets now. One is Borel measurable set and other is measurable sets. Is that okay?
Yes, sir.
Now, once you have a topological space, or let us consider F from R to R, you know that F is continuous if and only if for every open set in R, the codomain R, inverse image is open. A continuous function is that which pulls back every open set to open set. Not it maps every open set to open set. It pulls back every open sets to open set. This is known definition. Yes or no?
Yes, sir.
Now,
Yes, sir.
therefore, suppose F is continuous. Then if you start with a open set in the codomain, let us say G, then F inverse of G will be
Open.
open. And you know that every open set is measurable. Yes?
Yes, sir.
Therefore,
Yes,
F inverse of G will be measurable. Therefore, for every continuous function, given a continuous function, F inverse of G will be measurable for every open set G in R. Do you agree?
yes, sir.
Please remember, please note that I have put only one-way implication. I have put only one-way implication. F is continuous implies inverse image of every open set is measurable because it is open. Inverse image of every open set is open. But when I say inverse image is measurable, I am not sure whether inverse image is open, right? Measurable does not mean it's open. Yes or no?
Yes. Yes, sir.
And hence I cannot say the reverse. If F inverse of G is measurable for every open set G in R, I cannot call F as continuous. Are you
Yes,
with me? Are you with me?
Yes, sir.
Yes.
Yes. For continuity, I need F inverse of G to be open for every open set G. Suppose I know only that F inverse of G is measurable for every open set G, then I can't say F is continuous. I can't say F is continuous. Okay. That is because every measurable set is not open. Okay. And if you want, I can given here a particular concrete example where inverse image of every open set is measurable, but the function is not continuous. Okay. So continuity implies that inverse image of every open set is open and hence in particular measurable. But if inverse image of every open set is measurable, I cannot say function is continuous, but that I will take as definition of measurable function. Okay, now I have measurable function. So look at the precise definition. You have a measurable space x comma a. So what is a there? If you have a measurable space, what is a there?
Sigma algebra.
Sigma algebra. It is just a sigma algebra. And suppose you have a topological space. y comma tau. Okay. So in the domain, you have a measurable space, and in the codomain, you have a topological space. When you are talking about function from R to R, you can say that in the domain, I have Lebesgue measurable space, and in the codomain R, I can treat as a topological space. Yes or no? Because R is also a topological space. Are you with me?
Yes.
So instead
Yes,
of
sir.
f from R to R, I have now from X to Y, where domain X is endowed with a sigma algebra and codomain Y is endowed with a topology. Okay. Now you take a open set in the codomain. I can talk about open set because I have a topology. Take a open set in the codomain, that is G, and suppose inverse image is measurable for every open set in the codomain. I call such a function as measurable function. Okay, so now I am making a slightly different definition, but it will coincide with the definition that we made. The definition that we made for measurable set, measurable function, f from R to R was different. Can somebody recall what was the definition we made for measurable function from R to R? When will you call a function from R to R measurable?
Inverse image measurable.
Pardon?
When inverse
Can,
image measurable.
no, that was not the definition we made actually. The definition we made was collection of all x such that f of x greater than alpha, or f of x greater than or equal to alpha, or f of x less than alpha, or f of x less than or equal to alpha is measurable. Yes or no?
Yes.
But that is equivalent to say that inverse image of every open interval is measurable. And that is equivalent to say that inverse image of every open set is measurable. Okay. That is from R to R. Now, if you have a general function from a sigma algebra to a topological space, we will define measurability like this. Inverse image of every open set is measurable, because in the domain I can talk about measurable set, and in the codomain I can talk about open sets. Okay, because codomain I have assumed as topological space. You should see this parallelism. In topology, the basic ingredient is topological space and continuous functions. And what is continuous function? It pulls back every open set to open set. In measure theory, the basic ingredient is measure space and not continuous function, but measurable function. And what is measurable function? It pulls back every open set to measurable set. But here let me make also a comment. Why I define like this is codomain I have made as a topological space, because later we will be considering only real valued function and complex valued function. And in real and complex, you already have a topology. Okay, that's why I have defined measurability like this. But instead of having a topological space, you may have only domain and codomain as measurable space. I repeat, you may have domain and codomain as measurable space. In that case also, I will define measurability of a function like this. But only difference is, instead of calling it pulls back every open set to measurable set, how will you define? Can you tell me the definition?
Measurable set is measurable.
Every measurable set to measurable set. That will be the definition. Okay, I repeat. I made the definition in case the domain is measurable space and codomain is a topological space, because later I will be considering only real valued or complex valued. But in general, you can talk about measurability when the domain is also a measurable space. Codomain is also a measurable space, need not be a topological space, need not have open set concept, etc. In that case, my definition would be A function from a measurable space to measurable space is said to be measurable if there are too many measurable. It pulls back every measurable set in the codomain into a measurable set in the domain. Is that okay?
Yes, sir.
Yes, sir.
So in particular, if you have a continuous function from R to R, do you see that it will be measurable?
Yes, sir.
Because it will pull back open sets to
Open sets.
open sets, and but open sets are measurable. Okay. So I will not go for measurability of a function between measurable spaces. I will go only for measurability of a function between a measurable space and a topological space, because later we will be considering only real valued or complex valued function. Okay. Now, this is what I want to talk about abstract measure spaces. So what is sigma algebra? What is measure? And what is measurable function? Okay. Now, once you have a measure space, what is measure space? Set, sigma algebra, and a measure. Now you can talk about integration. Okay. Integration of a real or complex valued measurable function. So suppose you have a measure space. How did you define integration there? First you define for simple function, then you define for non-negative function, and then you have extended for any real valued or complex valued function. Yes or no?
Yes.
What was the
Yes,
domain?
sir.
What was the domain?
Measurable space. Measure
Ah.
space.
No. In our setting so far we discuss only R. F from R to R, where R is endowed with Lebesgue measurable set and Lebesgue measure. Okay. Now instead of domain to be R, we take it to be X, some set X, where X is endowed with a sigma algebra script A and a measure mu. So instead of R comma M, I have X comma script A comma mu. Is that okay?
Yes.
But now the functions are from X to R or C. Codomain is R or C. I am talking only about real valued or complex valued function defined on set X. Okay. Now I want to define integral of X, integral of F. Okay. Suppose F is measurable. F is measurable. Suppose F is measurable. So what do I do? First I define for simple function. Same technique. Only difference is instead of measure of AI, M of AI, Lebesgue measure, I will have mu of AI. Okay. And that will be called as the integral of simple function over the set X with respect to measure mu. Okay. Now, once I have it for simple function, I can have it for non-negative measurable function. Same way, take supremum. Is that okay?
Yes, sir.
And once I have
Yes, sir.
for non-negative extended real valued function, I can have it for any function by decomposing F as
A plus and A minus.
positive part and negative part. So this is the standard way. Simple function, non-negative measurable function, and general function, including complex valued. Okay, it can be complex valued also. So the same thing what we did for integration over R, now you can define integration over X, where X is endowed with a sigma algebra and a measure. Is that sounds good?
Yes, sir.
Just for sake of exposition, I have written all these details here. Okay, so now you should not say we have not dealt with abstract integration. Yes, we did it. Once you are strong with Lebesgue integration over R, abstract integration is not something new. Everything works in a similar manner. Okay. Yeah. Now, after defining integration, what did you study majorly is convergence theorem, right?
Yes, sir.
Monotone converge. Basically, the question is, if you have a sequence of functions fn converging to f, can we say integral fn converges to integral f? Okay, that is the basic question, convergence theorems. Okay, and there are positive answer to this question with some assumptions, additional assumption. In general, answer is no, but answer is yes with some additional condition. And that main three theorems: monotone convergence theorem. Without any assumption, you have Fatu's lemma, namely you cannot talk about limit, but you can talk about limit infimum. And the most useful case is dominated convergence theorem. So these are the three cases. And all these three cases work well, not only for functions defined on R, but functions defined on any set X, provided you have a sigma algebra and a measure space. Measure. That is, I can say on any measure space X. Is that okay?
Yes, sir.
Yes, sir.
I have written down the statement. The statement and the proof go word by word. There is no difference. Whatever we did for R to R, we can do for X to R. Remember, the codomain should be again real or complex value. Because if the codomain is arbitrary set, then these things doesn't make sense. The starting point is simple function. Okay. Now for simple function, you are writing it as summation I is equal to 1 to n alpha I. Okay. If the simple function is from X to R, this alpha i's will be real number. So that you can talk about alpha I times measure of ui. Are you with me?
Yes, sir.
The product you can define alpha I times measure of ai. However, if alpha i's are in a general set X, if alpha i's are in a general set X, then there is no multiplication, right? Mu of ai will be in R and alpha i's will be in general set, and you don't have a multiplication. So things will not work as you think. Are you with me?
Yes, sir.
That's why we don't take function from X to Y or X to X. We take function from X to R or X to C. Okay. Domain can be any measurable space, but for integration theory, at least for now, I need codomain to be scalar valued, real or complex valued. Okay. So all the convergence theorem works well, and all these things I have written. I didn't prove it. Proof goes exactly similar. So what is important is to understand the statement and how we can apply it. Okay. So those things I have recorded in this lecture. That's what I called as part A. Okay. So this is nothing new except that we are making a attempt to work with a general setting from our knowledge on R. Okay, that's the only thing. If you don't like to take x comma script a comma mu, you can take r comma m comma mu m to understand the things and then push it to x comma script a comma mu. Okay. As I told you, there are two ways to do mathematics. First, introduce abstract things and then go for concrete example, or do it the other way. Familiarize yourself with many concrete examples and getting the feel of it, go for abstract theory. I always admire the second thing, getting examples first, work with particular cases first and then go for abstract. That's why I did like this. Okay. So with this, the first part of this lecture is over. It was nothing new. Now, in the second part, I am going to introduce what is called as Lebesgue spaces. Okay. I don't think half an hour will be sufficient. So I may continue with the tomorrow's tutorial, and something we will do with tutorial. Maybe I can give you, I can put the hints to those solution or something like that. Okay. So more than tutorial, I will give importance for this LP spaces, because LP spaces are going to be chief examples of many concepts that you will study in the next course, next semester course, namely function analysis. So both probability and function analysis, measure theory going to be a prerequisite. Okay, so if you are not strong with measure theory, you may not be able to enjoy function analysis for sure. And probability depends. Some people do probability without touching much on measure theory also. Okay, so that depends how people handle it. But anyway, but essentially both probability theory and function analysis need measure theory. Okay. So I will give more importance for at least an overview of what is called as capital LP spaces. L stands for Lebesgue. Okay. Anyway, I am going to introduce it. So let us start at least today. Maybe by tomorrow's tutorial, I can finish it. You will study it again in the function analysis, but this is the right venue to at least introduce it. So I would request all of you to recall your course in real analysis. Okay, and tell me what is the basic setting or the basic notion that you have studied in real analysis. All other concept you have studied in real analysis is based on this particular concept. What is the fundamental concept in real analysis? Can somebody remind me?
State, sir.
Pardon?
State theory, logic.
Set theory. I am asking you the setting. Set theory is going to be fundamental in all branches of mathematics, no doubt about it. But in particular in real analysis, about what you learned, about what? You talked about convergence, you talked about compactness, you talked about connectedness, you talked about Cauchy sequence, you talked about completeness. All these things are on which, what? I cannot limit. No, still you are not understanding my question. The basic setting in a real analysis is not limit. How do compactness is connected with the limit? Connection comes later, but compactness is defined for what?
Point.
Points.
Set, sir.
Sets in where?
R.
Only R? Sets
R,
only huh?
R to RK.
Only that? Only RK you dealt with? Anyway, I don't think I will get an answer. It is very disappointing. You should immediately answer. A basic setting in real analysis, metric space. You are talking everything based on metric space. Yes or no?
Yes, sir. Yes.
You have X comma D. This is the basic setting. And then limit, everything comes later. Why you want R? Again, R is with absolute modulus. It is a metric. It is a special case. Okay. I don't know how you are studying different subject without entering into its core, basic. Okay. Anyway. So recall that fundamental concept in, I will even put it in writing, because I did not get answer from any of you. recall that fundamental notion in real analysis is that of a metric space. Do you agree? At least now, do you agree? Now, starting point was that. Then you talk about open set, closed set, convergence, whatnot. Say x comma d. Now, what is x? What is x?
Non-empty set.
Just a non-empty set. So when you talk about metric space, we don't demand any structure on X. X can be any non-empty set. Okay. Note that we don't demand any structure. You will understand what I mean by structure. Any structure on X, and X is just a non-empty set. And what is D? What is D? In a metric space, what is D?
Function distance.
The name is distance, and it's a facility to talk about distance between 2 points. And basically, it is a function. D is a function from X cross X to R, right?
Yes, sir.
Satisfying certain requirements. And how do this requirement is being imposed? The requirement is being imposed by looking at our own experience of measuring distance between points in R, or distance between points in R2, or distance between points in space. Our experience of measuring distances between 2 points in plane or space guided us what are all the properties that we should demand on D. Yes or no?
Yes, sir.
And further, we do not demand that D satisfy some special features. We don't demand D satisfy some special features except for a few conditions guided by some. Of course, there are some conditions like a triangle inequality. D of xy should be equal to 0 if and only if x is equal to y, things like that. Okay, a few conditions guided by our experience of measuring distance between 2 points in R, or R2, or R3. Okay, so we demand that D should satisfy certain conditions, but apart from those 2, 3, or 4 conditions, we don't demand anything else on D. Yes or no?
Yes, sir.
So I repeat, the fundamental building block for real analysis is a metric space. And while talking about metric space, immediately it should come to your mind, it is a pair x comma d, and there is no requirement on x except that it is a non-empty set. And there is a few requirements, there are a few requirements on d, but apart from that, there is no additional feature imposed on d. Something like D should come in this way, in a particular way. Nothing like that. D is a function satisfying certain conditions. That's it. Okay. That is on one hand. Now, on the other hand, you have learned linear algebra. What is the fundamental building block in linear algebra? No, you don't have any answer. In linear algebra, what is the basic notion that one starts with? You have done a course, right? Nobody wants to say? What is the fundamental notion that you learned in linear algebra, based on which all other concepts are being discussed?
Vector space, sir.
Vector spaces. So that is the fundamental building block, right? In linear algebra, the fundamental notion is that of vector space. And what is vector space? Again, I don't want to go for the details, but at least you should understand that the notion of vector space is being motivated by our experience of vectors in plane R2 or vectors in space. Okay. Vectors in space give us an idea of how to define a vector space. It is not just playing with words, but you should understand what I mean. We have some experience of dealing with vectors in R3, vectors in space. With that knowledge, we abstracted and made the concept of vector space. Yes or no?
Yes.
So, and in vector space, what are the things you can do? Mainly, you can do two operations. You can add vectors and you can scale vectors. You can talk about x plus y. You can talk about alpha x. Do you agree?
Yes, sir.
Now, what we do is, in some situations or in some cases, of course, for metric space, you need your underlying set X to be just a set, no need of any structure. But in some cases, we will look for metric spaces where that set X has certain structure. For example, that set X could be a vector space. For instance, R2 itself is a metric space, and also you know that R2 is a vector space, right?
Yes, sir.
But so far you have never attempted to make some interaction between them. In real analysis, you considered R2 as a metric space. In linear algebra, you considered R2 as a vector space, and you never attempted to make any interaction. Are you getting me?
Agree, sir.
Yes or no?
Yes, sir.
So what now we are going to do is, we are going to consider metric space XD where the base set X, the carrier set X, the underlying set X is not just a set, but it is an algebraic structure. And we will demand that the distance comes from, or distance satisfy certain special features. Okay, so let me try now. In some cases, we shall demand that in a metric space, XD, X has some structure, not just a set, it has a structure. For instance, you can add two elements in X. You can multiply an element in X with a scalar, maybe. Something like X is a vector space. And D has some special features we may demand. And one such instance is the following. One such instance is the following. I take X to be vector space. Basically, it is a set. But instead of just set, I am taking X to be vector space. For instance, R2 or R3. Vector space over a field. But now I am restricting my field. Field is K, where K is either R or K is C. So field is either real or complex. So X is a vector space. Okay.
Okay.
So now X is not just a set, it is a vector space. And the metric on X arise in a particular manner. Further, that is my demand. What is that particular? I will do. I will tell you. Further, the metric on D, this is only one instance, okay? Arise in a particular manner. Now, what is that particular manner? To understand it, go back. Now, set X is not just a set, but it has a structure, namely, it is a vector space. Now, if you recall, the idea of vector space itself is motivated by vectors in space or vectors in plane. Okay, you can add two vectors, you can multiply a vector with a scalar and so on in R2 or R3, and those ideas give rise to an abstract setting vector space. But while moving from vectors in plane to vector space, I repeat, while moving from physical vectors in plane to the idea of vector space, we considered only addition of vectors and multiplication of vector by a scalar. But if you look at R2, you also have the notion of length of a vector. Yes or no? In fact, in physics, you have defined vector as those physical quantity having both magnitude and direction. So in vectors in plane has a magnitude, has a length. Do you agree?
Yes.
But while abstracting into vector space, we did not consider that aspect. We considered only addition of vectors and we considered only dilation of a vector by a scalar. We did not look into the aspect of length while forming the concept of vector space. Am I right?
Yes, sir.
So let me repeat. While forming the general concept of vector space in linear algebra, we have completely discarded the idea of length of a vector in R2. That part is not at all taken care. Okay. Now let us take care that also. Okay. Note that we have notion of length for a vector in R2, not vector in vector space in R2 or R3. But what basically length does, okay? It takes a vector and it gives you a quantification, a number. Am I right?
Yes, sir.
given any vector, length gives you a quantification for that vector, a number with that vector. And that number should satisfy certain condition. Okay. So number, the magnitude is always greater than or equal to 0. Do you agree?
Yes, sir.
And when will be the magnitude to be 0? Only when that vector is
0.
zero vector, right? So let us look at our experience of length of a vector in R2. And guided by that experience, now we can define length for a vector in vector space as a function. Okay. Now let us define a notion of length for vectors in vector space. Again, how do you do that? By checking what we had in our simple concrete cases. This is common in mathematics. Vector space is formed by looking at vectors in plane or vectors in space. Measure concept is formed by looking at the idea of length of intervals or area of rectangles and so on. The topological space idea is formed by looking at what happens to open sets in R, open sets in R2 and so on. So this from concrete example only we make abstract concepts. Anyway, so look at the length concept. So what length does? So let nu be a function from X to R. So X is a vector space, okay? X be a vector space over K. K is R or C. Let nu be a function from X to R such that nu satisfies certain conditions. 1. Nu of X. Length of any vector in R2 is greater than or equal to 0. So that I impose as a condition. Nu of X is greater than or equal to 0. Nu of X is 0 if and only if X is 0. This 0 means the 0 vector in X. Okay. 0 element in X. Now, what is X? What is X? What is the assumption on X?
Vector.
Vector space. X is not a vector. Capital X is a vector space over K. Okay. So X is a vector space. And now you are doing something with a vector space. So whenever you do something with a vector space, you should say what happens to fundamental operation available in the vector space. Then the fundamental operation available in the vector space are vector addition and scalar multiplication. So I should say how this new function act on scalar multiplication, how this new function acts on vector addition. Okay. So nu of alpha x, I demand that it should be equal to mod alpha times nu of x. The length of 2x vector should be 2 times length of the vector x. Okay, this is true for any complex number alpha. And remember, in the right hand side, you have mod alpha. This is the dilation. And suppose I find nu of the sum, length of the sum, x plus y, what I should get? Look at R2. You have two vectors. You add the length of first vector and add with the length of the second vector. What you can say?
Less than equal to nu of x.
It will not be equal to. This should be less than or equal to nu of x plus nu of y. And this should be true for all x and y in x and alpha in k. If a function satisfies these conditions, we call that function as length, or more standard terminology is norm. Okay. Such a function such a function nu is called, give me 5 more minutes, is called a norm or length. And it is usually denoted by this is the symbol. Instead of writing nu of x, I write it as this. Double line x and called norm of x. Okay, read as norm of x. And so you started with a vector space and you seek help of a function nu satisfying these conditions. That nu will define length, and now you have a notion of length to a vector space. The pair x nu is now denoted like this, is called a normed linear space. Vector space and linear space are same. Linear space is another word for vector space or normed vector space. You had a vector space. Now with the help of nu, you have normed it. You have made the concept of length. Okay. Is that okay?
Yes, sir.
And this is the fundamental notion that you will start with in the course function analysis. Okay. This turns out to be the fundamental notion in function analysis. Why I told all these things? Let us see function analysis. Why do you want to, at this juncture, why is it important? Okay. Now, if you remember, my interest was to get a metric space in which the underlying set has a special structure, maybe vector space, and a metric comes in a special manner, special feature it has. Now, remember again R2. In R2, you have length of a vector. And can you talk about distance between two vectors in R2? Distance between two vectors in R2, d of xy.
Yes, sir.
How do you do that? You take the difference between x and y. That is, you talk about x minus y and then take its length and then take its length. That will give you distance between x and y. Am I right?
Yes.
So basically, the length notion gives you distance notion. So now, having got norm notion of norm, you can define distance now. Let X norm be a normed linear space. Be a normed linear space. Okay. For two vectors x and y in X, what is normed linear space? It is a vector space along with a norm function that will facilitate us to talk about length of a vector. Now for x comma y in X, define d of xy. Can you suggest what should be my definition?
Norm of x minus y.
X minus y. This length of x minus y. Is x minus y defined? Yes, because I am in a vector space. X minus y is defined. X minus y is again a vector, and for any vector, since I am in a normed linear space, I can talk about the length. Okay, so I define like this. Okay, and you can see that this D satisfies all the requirements of a metric. Okay, it turns out that it's a good exercise. Okay, it turns out that D satisfies all requirements of a metric. The properties that you have imposed on nu will get translated to the property that you want for a metric. For instance, d of xy is equal to d of yx. All these things you will get. So what is the message? The message is that once you have a normed linear space, you automatically get a metric space. Yes or no? And hence,
Yes.
xd is a metric space. To put in simple language, every normed linear space is a metric space. So now I have a metric space in which the ambient space, the underlying set, is not just a set, but it is a vector space. Do you agree?
Yes.
And the metric is not just a metric, it has some special feature. It comes via how did you define D?
Norm.
Via norm. But remember, the norm has some interaction with scalar multiplication and vector addition. Therefore, this D has some interconnection with the structure that is available on X. Do you agree?
Yes.
Yes.
So now you have a metric space in which the ambient space is not just a set, but it is a linear space or a vector space. And the underlying metric is not just some metric, it comes via norm, and this norm has some interaction with operation available in the vector space. That much is clear?
Yes, sir.
So there is some interconnection. There is a linear algebraic aspect and there is some metric. So this is called a normed linear space. Every normed linear space is a metric space. What is the big advantage? If you take a metric space like this, namely a normed linear space, then the underlying set is not just a set, but it is a vector space. So you can import all the things that you have learned in linear algebra to a normed linear space. You can import the linear algebra knowledge to the normed linear space. Agree?
Yes, sir.
Now, a normed linear space is also a metric space. Agree?
Yes, sir.
And therefore you can invoke all the results that you learned in linear algebra for a metric space can be imported to a normed linear space.
Yes, sir.
Yes, sir.
Thus, you can see the marriage between linear algebra and
Metric space.
analysis.
Real analysis.
Real analysis. And that is exactly what function analysis is. Okay, so function analysis, the basic ingredient is normed linear space. In a normed linear space, you have a linear space, you have a norm, and norm gives you a metric. Because of metric, you can talk about analysis aspects like convergence, compactness, connectedness, completeness, whatnot. And because of linear space, you can talk about basis, spanning set, linear independence, everything. So both the ideas of linear algebra and ideas of analysis merge together, interact together via the concept of normed linear space. Okay, so it's something like a marriage between real analysis and linear algebra, and that is function analysis. And the fundamental notion of function analysis is a normed linear space. That much is clear?
Yes, sir.
So that you will
Yes, sir.
do independently in your course, and our purpose is limited. I am going to give you some examples of normed linear space arising out of Lebesgue measure theory. Okay, so my purpose is just to give some examples of normed linear space, the so-called Lebesgue spaces. Okay, we shall provide some examples. Provide some examples for a normed linear space. I will write NLS. Okay. Arising from measure theory. So that I will do tomorrow. Is that okay?
Yes, sir.
So did you understand the concept of normed linear space? What is a normed linear space? It is a linear space. It is a vector space in which you have the definition of length. What is length? It is a function satisfying these property. What is it good for? Once you have length, you have distance. Once you have distance, you can import all the basic things that you have learned in analysis. So you can import both linear algebra and analysis. For instance, let me give you one instant and stop. You have talked about linear combinations in linear algebra, right?
Yes, sir.
Yes.
What do you mean by linear combination? Suppose I have a linear space or a vector space X. What do you mean by linear combination of vectors? So let us say x1, x2, x3, etc. xk are in a vector space capital X, and alpha 1, alpha 2, etc. alpha k are scalars. Then what do you mean by linear combination?
Summation of alpha x.
Alpha 1 x1 plus alpha 2 x2. Sorry, alpha 1 x1 plus alpha 2 x2 plus etc. plus alpha k xk. Yes or no?
Yes, sir.
Yes, sir.
That is linear combination. Okay, that makes sense because you have the operation of addition and you also have the operation of scalar multiplication, and you know. And you know that addition is associative, so I don't have to bother about the bracket. I can say x1 plus x2 plus x3 without putting bracket anywhere. Associativity will take care of it. Okay, but have you ever talked about alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3 plus etc. in linear algebra? I mean an infinite sum. Have you talked about an infinite sum in linear algebra?
No, sir.
You will not, and you cannot, and you should not. Reason is, if you want to talk about an infinite series, let us say x1 plus x2 plus x3 plus etc. To talk about infinite series, you need the concept of convergence, right? How do you talk about series? It is via convergence of sequence of partial sums. So without having the notion of convergence, you cannot talk about infinite series. Do you agree?
Yes, sir.
And to talk about convergence, you need a metric. Do you agree?
Yes, sir.
But in a linear space or a vector space, you don't have an idea of metric. You have only a plus and dot. You don't have a metric. So you cannot talk about series or, roughly speaking, infinite linear combination. It's a bad word because linear combination by definition itself is finite. Okay. So, but if you understand, I can take the liberty of using the word infinite linear combination. You cannot have a concept of series or an infinite linear combination in a vector space because in a vector space you don't have a metric. But now you have a vector space with a metric. What is it?
Normal linear space.
And hence in normed linear space, now you can talk about not only finite linear combination, you can also talk about
Infinite linear combination.
infinite linear combination because you know how to talk about convergence via metric. Okay, so this is why you have an extension from linear algebra. It's not just linear algebra. So you can take the advantage of having a vector space. You can take the advantage of having a metric. you can merge it, and that is what gives you normed linear space, and hence you can see nice interaction between linear algebra and real analysis in our function analysis, in your function analysis course. And of course, when I talked about function analysis, I will become more and more enthusiastic. It is my favorite subject, and I also work basically on function analysis. Anyway, so my purpose is just to give some examples of normed linear space arising out of measure theory. Okay, that I will do tomorrow. And basically, I am interested in what is called as Lebesgue spaces. Lebesgue spaces. Is that okay?
Yes, sir.
And these spaces will come as examples for each and every notion that you will learn in function analysis. So it will not be nice to avoid Lebesgue spaces and do a course on measure theory, because next time people may assume that you already did a course in measure theory and you are aware of what is Lebesgue spaces. So with that intention, I will just briefly introduce the Lebesgue spaces tomorrow. And unfortunately, I may not be able to take the tutorial. So I would suggest that I can go add some more problems to that sheet, and whatever we have not discussed, I can put either the solution or a detailed hints. Does it sound good?
Okay, sir.
And so up to Lebesgue spaces will be the content or the syllabus for the examination. But again, a decent course in measure theory should also introduce product spaces and product measures. So I will do it in 1 or 2 lectures, which will not be given as live lecture. I will record it and post it in Moodle. Those who are interested can watch it. But that will not be a part of examination. Is that okay?
Yes, sir.
Yes.
So product measures and Fubini's theorem, that I will 1 or 2 lectures I will do and put it in Moodle. So in tomorrow we will discuss Lebesgue spaces, and tutorial. There are some few more problems that I have to discuss, and I wanted to add a few more problems, and those problems which we have not discussed and which are yet to add, I will do it with hints and solutions. Okay. With that, let me stop.